This presentation will cover cable ampacity and sizing as it pertains to the ANSI standard. So the agenda for this presentation, we're going to be going over a brief cable systems overview. We're also going to go over the various cable standards, again just an overview, and we're going to go over the software graphical user interface, so essentially how to perform the cable ampacity and derating and sizing using a software like ETAP. So the cable systems that are supported in ETAP vary from the network analysis, which is what we're going to be covering today, which in turn goes over how to perform a voltage drop, how to when doing a short circuit study, a motor starting, harmonics, all of those cable related analysis would fall under network analysis. There are also, if you look on the bottom left, thermal analysis, which essentially is a cable temperature ampacity calculation for underground raceway systems or direct buried. So that's that would be covered under thermal analysis, which would be a different presentation. And then over on the right hand side you have the mechanical analysis, which is cable pulling, the sidewall pressure calculations, as well as the tension. So that is again the mechanical analysis. It's covered under a different ETAP analysis module and presentation as well. So let's go ahead and focus on the network analysis, and the way we're going to start the presentation is by giving a brief background. As all of us know, proper sizing and current derating of cables makes sure that they operate to their maximum potential while providing secure and reliable operation. So let's start by providing the fundamentals, which is the cable ampacity, which is essentially the maximum amount of electric current a conductor can carry before sustaining immediate or progressive over time due to exceeding its temperature rating. So it's very important to properly derate and size cables, otherwise we shorten the life of the equipment. For IEC users, which would also could be covered on a different presentation, British standards, IEC, the cable ampacity is also known as the current carrying capacity, or just capacity. But for the purpose of this presentation, we will call it cable ampacity, since we're going to be covering the North America standards, or 60 Hertz / ANSI standards. The heat is generated when current is carried through a conductor. So it must pass through the electrical resistance of the conductor, which in this case is copper. And there is a brief calculation there of watts, which is I square times the resistance, or R. And some of the thermal limits on a cable cable ampacity thermal limits, as we could see from the picture, is essentially the cable construction, the installation type, whether it's underground, above ground. Very important is also the ambient temperature, because this will have a direct impact on heat dissipation. The grouping effect, especially how when we have it on a cable tray, or if we have them on a particular cable tray or underground. Other thermal sources would also have an impact, like if there's a steam pipe near the cable installation, and of course harmonics, which essentially, if we have harmonics other than the fundamental, it will increase the heat in the cable. So the standards that we're going to be covering today are the almost like you could say table lookup methods, so the IEEE 399 or the Brown Book, also the ICEA P54440, which is for cable trays, and the NEC National Electric Code, which is again also a table lookup method. All of these table or based standards take into account the thermal limits as shown on this particular slide. So now the question is how to determine the proper cable capacity so we could size our cables properly. Number one would be based on the manufacturer's base ampacity. This would essentially be the correction factors. This is typically how the IEEE 399 or the Brown Book is going to work. The manufacturer provides us with base ampacity for a given installation. We then apply the various corrector factors based on the installation and other factors, ambient temperature and such. Also the ampacity tables using standards and the rating factors. This is more for like NEC and ICEA P54440 standard, where the standard typically provides us with ampacity tables, also with installation tables, so we can go there and look it up. Also, and this is not part of this presentation, but also thermal analysis using the Near-McGrath method, or IEC 60287, can also be performed to come up with a thermal analysis to squeeze the most performance out of our cable installations. Again, this is going to be the thermal analysis will be a separate presentation, but it's important to highlight it at this point. Cable installations that are supported in ETAP are shown here. Over on the right hand side, we have the standards that the first three is what we're going to cover for this presentation. The next two, which are the British Standard and the IEC, those would be covered on a different presentation. But essentially, let's cover the ANSI or North America cable installation standards supported in ETAP. So we have the IEEE 399, which is also known as the Brown Book, and it provides the rating factors for direct buried as well as duct banks. This standard is mostly used for industrial applications, typically on medium voltage cables, cable applications. Next would be the ICEA P54440 standard, which is for above ground cable trays, or on cable trays. Essentially, this standard is used more on commercial applications. And the next standard we're going to cover is NEC. This is essentially the base ampacities provided to us in Article 310. This is for above ground trays, above ground conduits, and airdrop. This is the type of installation as provided to us in the NEC. What we're going to do in this presentation is essentially perform a cable sizing using these methods in the software. So what I like to do now is turn over to the software and begin performing a cable ampacity and sizing calculation. I have a single line diagram open. This is the latest version of ETAP. What we're going to do is we're going to go from the edit mode to the load flow analysis mode. And the first thing I'm going to perform is going to be a load flow analysis. So I perform a load flow analysis, and the first thing that I notice is I could see my power flow values expressed in amps. And over on the bottom left, I see my alerts showing cable number 2 right here. Is showing cable number 2 as being overloaded. It says that the limit of the cable, this is basically the ampacity, is 89.3 amps, but it's operating at 288 amps. So it's overloaded by about 323%. anytime a cable is reaches or is overloaded to more than 100% of the rating or limit, ETAP will flag it as an alert. You could think of it as when the operator gets an alarm for an overload condition. It's essentially the same. Very similar alert that when you perform a load flow analysis, any cable that is overloaded, transformer or protected device frame would automatically be displayed in red on the single line diagram, and also highlighted in the alerts view, the same way that I'm showing right now. So the first thing that I like to do is I could double click on cable 2 from the alert view. This would in turn provide me with the cable characteristics. Okay, and the first thing that I'm going to do is I'm going to look at the installation. So for this particular cable installation, we're looking at IEEE 399 or Brown Book, and this is using an underground duct installation. Now for my grouping, if we go over to my rows and my columns, this would be, if for those of you who are familiar with underground ducts, you have the number of rows, which would be the horizontal, plus the columns, which are vertical. So this happens to be a 2x4 installation. And then over on the right hand side, we have what the operating, the base, and the derated values are. So operating means the results that are coming from power flow or load flow. The base is based on the ampacity that is provided to us by the manufacturer, and then the derated is after applying the multiplication factor from the after applying from the multiplication factor from the grouping and also the ambient temperature. So we could see that the allowable ampacity as the derated for this cable size 1 is 89.3 amps. Now in order to properly size this cable, we need to have 3 items selected. We want to make sure the standard is selected, we want to make sure that the installation has been selected, and we want to make sure that the grouping has been selected, and also the derated is set, because you could also have a user define. So for those of you who maybe instead of using the derated option as shown here, perhaps you have an internal derating table that you want to use for your project, you can always select the user define and then specify right here your defined ampacity. This is important here to mention, because this value, whether you have the derated selected or user defined, would in essence become your rating or your limit as shown on the alerts. So anytime you perform a load flow ampacity and the actual amps flowing through that cable or transformer, in this case a cable, the amps flowing through that cable because of the connected loads downstream of the feeder, ETAP will do a comparison. So it'll compare the rating or the limit displayed here versus the operating amps, which are calculated by load flow analysis, and it'll provide you with the alert as shown below. Okay, so that's essentially how the alerts is able to come up with the report as shown on the bottom of the screen. Now, I'm going to close out of this window here. If we're doing cable sizing, so what we're going to do now is we're going to perform a cable sizing for cable number 2 based on the connected load. And the first thing we'd like to do is after you run switch over to the load flow analysis mode, it's important to go into the study case. once you open the study case, you go over to the bottom under the update section, and then there is an option called cable load amps. So we're going to make sure that this is selected in order to update the actual amps flowing through the cable inside the cable editor page. And this is very important because that would become now our base for performing the cable sizing, right? In this case, cable load amps would update these 288.6 amps into the cable loading page. So that would become now our the value that we're gonna use for sizing cable number 2. So after we check the cable load amp option, we click OK, and we rerun the load flow analysis. We now go into cable editor page. So we double click on the cable from the single line diagram. We head over to the loading tab. So we're inside the cable editor page. After we go over to the loading page, you notice that we have 3 options under loading current for sizing. Again, we are about to properly size cable number 2 based on the installation, based on the underground installation, and also based on the loading conditions that are downstream of this cable. So you have 3 options. The option that is currently selected means full load amps of element. This option here is useful for transformers or for cables that are feeding a motor, or for cables that are feeding a transformer, for example. And the reason why is because ETAP will automatically sense the rating. In this case, it is sensing the switchgear rating at this bus location. If this cable was on the line side or the primary side of a transformer, it would sense the primary full load amps of the transformer and provide that value here in amps. The user is also free to select any other element from this table, but the default full load amps of element is the device that is directly connected to the load side of the cable. Okay, in this case it would be sub 3 switchgear, which is this bus that is representing the switchgear, which is rated at 600 amps. The other loading current option is user defined. So if you would like to provide your own user defined ampacity or rating for the equipment that is downstream, you can also specify that in this case, and also as the a percentage factor. So just to get the kVA correctly. And the option that we mostly use, and this is what we're going to be using for today's example, is going to be the operating current. So we're going to select operating current. You notice that the amps and the power factor have automatically been imported. In fact, these are not user defined. These fields are automatically populated. Number 1, from the load flow results, the load flow report. Whenever you go into the study case, as we did earlier, and then check the cable ampacity option. That's why it's so important to always go into the, here, let me highlight that one more time. That's why it's so important to have this option here checked, the cable load amps. Okay, so quickly going back to the loading tab, we want to make sure that we have the operating current selected, and that in turn will provide us with the operating load current for phase A, B, and C. Again, remember, we're assuming this is a balanced 3-phase system. That is the reason why phase A, B, and C come up with the same average. All right, so after we set up our base initial loading of 288.6 amps, so here it is shown on the single line diagram. Here it is showing in the cable editor loading page. The next thing we're gonna do is we're gonna go over to the ampacity, and if you remember from earlier in the presentation, we said we need to select 3 items from this page. Your standard. In this case, we have selected the IEEE 399 standard. Other standards include NEC, and for this particular cable, also IEC. Item number 2, we need to select the installation type. So some of the installation types that are available for this cable would be underground duct, underground buried, above ground trays, above ground conduits, airdrop, and IEC. Whenever you select the above ground trays, for example, the ICA, depending on the cable type you see selected, would appear for your standard. Again, we're using an underground duct as the installation for this particular cable. And the last item, number 3, is that we need to specify would be the grouping. So if we had, for example, 2 rows and 2 columns, we could change this from 2 rows and 2 columns. You could see over on the right hand side that the rated will automatically change. Now, the more rows and the more columns that we have. So, for example, we have 2 rows and 2 columns. Our derated ampacity is 109 amps. If we increase the number of columns to 4, for example, our derated ampacity now drops to 89. And the reason for that is because, as we saw on the slide earlier for the thermal limits, we now have a larger amount of cables and conduits, and it takes longer for the heat to dissipate, so the derated ampacity will drop. Okay, make sure that also the derated option is selected. So in this case, our derated 89.3 amps will be compared to the loading ampacity. All right, so now that we have the ampacity tab selected, let's head over to the sizing phase tab. Okay, and under constraints, it is important to have the loading constraint as well as the maximum voltage drop taken into account. So I'm going to go over these 2 options now. The loading constraint comes directly from the load flow results. It comes directly from the loading tab. This is the 288.6 amps as shown on the load flow results on the single line diagram. But also, most importantly, is the maximum voltage drop. And this is important when you have really long cables. This particular cable here, if we go on to the info tab, you notice has a length of 222 feet. So perhaps, not the longest cable run, but once you get into the really long cable runs, maybe closer to 3,000, 5,000, 6,000 feet, the voltage drop may become a real issue. So as per NEC, we have to meet a 3% voltage drop through a branch, so you can adjust that constraint here. The nice thing about it is ETAP will also give you maximum length. So for example, if I say I want to limit my voltage drop to no more than 3% for this particular cable, you notice that ETAP provides you what the maximum length would be for 3% voltage drop. So the maximum length for this particular cable run is almost 1,500 feet, 1,485 feet. So any cable length longer than that would essentially put us over the 3% voltage drop. Okay. Now, moving up on the same window here, let's take a look at results. So we now have an optimal size, right? The optimal size that has been calculated for this is 2 cables in parallel, size 4/0. So right now we are at, if we look at the pull down menu, we are at a size 1 a size number 1 cable. So and that's the reason why we had an overload condition, because it's not properly this cable does not support the 288.6 amp of loading. So what ETAP is suggesting, based on the loading and the maximum voltage drop constraint, is that we put a size 4-aught in parallel. So two sets of 4-aught. That would provide us with an ampacity of 298 amps and a voltage drop of about one tenth of a percent. Okay, so we're gonna select the optimal size. ETAP also provides a one size smaller option. A lot of times the equipment, when we're doing sizing, we have to take into account 100% loading for motor loads, and in fact, when you're sizing an MCC, you typically would want to use also the multiplication factor for ampacity, which is 1.25% to the largest motor on the MCC. We're not sizing an MCC for this particular case, but that option is also available. So in this case, as soon as we go into the optimum size, ETAP will change the database, and this pull-down menu will automatically reflect the new optimal size. We could go one size smaller depending on the project. Again, when you're doing this type of sizing, we take into account 100% loading, but many times we understand that the loading will never surpass more than 70 or 80%. So perhaps one size smaller, may actually save some money. ETAP clearly displays that if we go one size smaller, the ampacity, the maximum ampacity that it would be able to that we could support is 262 amps. The current ampacity that we have based on the load flow results is 288. So we're gonna go with the optimal size. One size smaller is also used sometimes on some distribution lines that could be overloaded for perhaps a brief period of time during maintenance or during bus transfers, perhaps. But for this particular example, we're going to select the optimal size. We're going to click OK on the bottom of the page, and then we're going to rerun our load flow analysis. And this device is no longer being shown as critical, so it's no longer being overloaded. So this is essentially a brief exercise on how to perform a cable sizing using IEEE 399, but the same applies if you're doing ICA P54440 or if you're doing the NEC standard. So with this, I would like to end the presentation. Thank you.